This is Chapter 9, Problem 62. The question reads, a 75 kilogram firefighter slides down a pole while a constant friction force of 300 newtons retards her motion. A horizontal 20 kilogram platform is supported by a spring at the bottom of the pole to cushion the fall. The firefighter starts from rest 4 meters above the platform, and the spring constant is 4,000 newtons per meter. Find A, the firefighter's speed just before she collides with the platform, and B, the maximum distance the spring is compressed. Assume the friction force acts constant during the entire motion. Starting with in order to start the problem, you have to find what's given. And what's given is the weight of the firefighter at 75 kilograms, the friction force, which is constant, at 300 newtons, the weight of the platform, which is 20 kilograms, the initial height of the firefighter, which is 4 meters above the platform, and the spring constant, which is 4,000 newtons per meter. And they want you to find for A, the firefighter speed, and B, the max distance the spring is compressed. So, in order to find the firefighter speed, you must first find acceleration. There are two components for acceleration. First one consists of the upward acceleration, which is friction, and then the downward acceleration, which will be more than the upward acceleration, but the downward acceleration is based off of gravity. So the upward acceleration can be found using Newton's second law. And in order to find Newton's second law, first you must find the force and the mass. So the mass is given as 75 kilograms for the firefighter, and the force is 300 newtons per meter. 300 newtons. So if the force is equal to mass times acceleration is equal to force divided by mass. So the acceleration here would be the force of friction divided by the mass of the firefighter. If you plug in those values, it's 300 newtons divided by 75 kilograms, and the answer will come out to be 4 meters per second squared upwards. Now, this is only the upwards unit. You still have to find the downward component. However, the downward component is merely acceleration. Again, this is the view here of net acceleration, which is acceleration downwards minus acceleration upwards. And acceleration downwards is just gravity at 9.8 meters per second squared, and the acceleration upwards, which we found earlier, is 4 meters per second squared. Given the net acceleration be 5.8 meters per second squared downwards. So you plug that into the general formula of v squared is equal to v naught squared plus 2ax. However, there is no initial velocity given she starts her slide down at 0 meters per second. Therefore, v naught would be 0. So if v naught's canceled out, you get v squared is equal to 2ax. You square root both sides. You get v is equal to square root of 2ax. Plug in the values. That would be 5.8 meters per second squared, and 4 meters, and your answer should come out to be 6.812 meters per second. Part B asks you to find the max distance the spring is compressed. Now, in order to find this, it's merely the conservation of energy, which is given as 1/2 mv squared is equal to 1/2 kx squared. If you were to plug in the values, you plug 75 in for the v, which we found in part A, 6.812, the k, which is spring constant, 4,000 newtons per meter, and then x is the unknown variable. And as you can see, the 1/2s would cancel out, and you would isolate the value of x. In order to do that, you would divide both sides by 4,000 newtons per meter, and then you would square root both sides considering the original equation was x squared. If you plug all of this into your calculator, you should get 0.933 meters, which would be your final answer for B.